Hello, ToobTimers. Well, we're back. And what are we going to do? We're going to take a look at all these Bumblebees that came out of that RCA radio. I removed all the Bumblebees in the first session or the first video of this series and replaced them. I replaced them with a modern capacitor. I forget what the dielectric is. Polypropylene, maybe? I don't know. Anyways, I thought we'd test them and talk about them a little bit. What I have is two modern capacitors and their equivalent sizes on the Bumblebees. Well, let's read this number first on here. If you notice, and I'm sorry, but it's very, very small, after the IC, or Illinois capacitor, you'll see a number 473. What does that mean? That means 47 with 3 zeros after it. 47,000 picofarads. That's how capacitors are generally based, in picofarads for non-electrolytics. 473, it'd be a 0.047 microfarad capacitor. And we're going to test this on the bridge. Now, what I have here is a Heathkit IT-28. It's my favorite bridge. It's a real workhorse. It's simple to use. It tests everything that's a capacitor. And you can still get them on eBay and places like that. And if you were interested in a capacitor tester and you don't mind manual or non-automatic operation, this is the fella to use. So let's talk about these controls for a minute. We have a selector switch. It talks about the type of capacitor we're testing, and what this does, it sensitizes the tester to the type of dielectric that's likely going to be in here. An electrolytic will be the leakiest of the dielectrics, where your paper and mica, etc., are the least leaky. Then there's a power factor knob that's used for testing the quality of electrolytic capacitors. Power switch, of course. We have range, a range switch that takes you from, in our case, 0.001 microfarads times the capacitance range reading, all the way up to times 1 for electrolytics, and an external scale for really large ones, and that'll take you to 1,000 microfarads. Okay, maybe not that big in today's society, but yeah, it's decent sized capacitors, particularly for old radio work. Then we have a voltage test. This voltage test will check the leakage of the dielectric. We have the modes of operation: discharged, no voltage on the terminals. We have a bridge, which we use to measure it, and then we have the leakage, in which we use to subject this voltage, subject the capacitor to the voltage on the indicator. In this case, I happen to have it set for 300 volts. But if we don't use the leakage, there's no sense in changing it. And the last switch is the generator switch. Internally, it has its own generator. This is an AC bridge, if you will, and it has its own generator. Now, sometimes with very poor capacity or very poor dielectric leakage factors or quality factors, dissipation factor, I guess that's it. With very nasty dissipation factors, you have to go into the external bridge mode because this unit can't supply enough current to test the capacitor in question. Now, there's 3 sets of terminal posts down below. This is an external standard. This is used in conjunction with this scale to compare your product against a known good component. This one is the external generator, which relates to this button, and we'll talk about that in a few minutes. You'll see it in action, actually. And then, of course, you've got the test set. I have here the neatest little test jig. It's from Grayhill. This little test jig it allows you to test leaded components very handily with banana plug connections. People have asked me where I have gotten this thing, And frankly, you just go on to eBay and you keep looking for your Gray Hill products, and eventually one will pop up for sale. That's how I obtained this one. I learned about this working many years ago in the lab at the factory where I worked, and they had a bunch of these things, and I thought they were just the greatest. Okay, let's get to testing. Now, what we have here is a 473 47,000 microfarad or picofarad capacitor, which is 0.047. So we're going to put our dial on 0.01, our times range, 0.01, and then we'll use the capacitance range, this first inner range, to see what the number is. I've got it set up for 0.47 right now, so you can kind of see 0.47 on the scale, on the hairline. You can kind of read it just before 5. And let's give her a bridge. First, let me take it off capacitance for a bit. We'll take it down to 004, and we'll put it in the bridge. Now, we're going to watch this eye tube, because this eye tube is the indicator when we should take readings or look at the leakage or whatever. So I'm going to close it up. Boom, the eye closes. Why? Because we're not at the right capacitance value. We have not balanced the bridge for this capacitor. So now we're going to slowly go. You have to really kind of go slowly, because if you go fast, you'll miss it. We know it's 0.47, so here's a 0.4, and we'll start creeping up, 0.45, 0.46, 0.48. Oh, there we go, right then and there, 47. And you adjust it for the maximum shadow window, which is about there, which is, I'll just say, I show 0.48. It's a little bit less than that, but it's sufficient for the demonstration. Now we put it back in discharge mode. Oh, by the way, you want to pay particular attention to this knob, because when you're in the leakage position, this voltage will be across these terminals. So if you have it set up for 300 volts, you've got 300 volts across these terminals when you're in the leakage mode. And believe me, it hurts. If you don't pay attention, it hurts. But let's check it for leakage at 300 volts. Watch the eye tube as I click it down to leakage. Boom, closes and opens real fast. What that means is there's no current flowing in the dielectric. No measurable current by this thing anyways. And that tells you if it's good. If it's a leaky capacitor, it will close. It will close all the way. Now this is a 630 volt. And we'll take it up to 600 volts because that's the highest voltage you can test. We're going to close it and you can see, boom, pardon me. It closes, the eye closed and opened back up. There's 600 volts on this thing right now. So we just kind of keep our fingers away. And then we open it back up. Now the discharge does exactly what it says. It shorts out these terminals, which makes it safe to touch. Bink. Okay, so now we know we have a good reading with this capacitor. Now we'll get out the Bumblebee. Now the Bumblebees are fairly easy to read. First you got to know which end to start. Because there's a big space here, that's telling you this is the voltage code. So what we're going to do is we're going to read it from left to right, realizing this big space is a pointer to where the left-hand side is. Yellow, violet, orange. 4, 7, 3. Yellow is 4, violet is 7, orange is 3. So this is a 473 47,000 picofarad capacitor. It reads just like a resistor, and it's easy to read once you sort of learn how to read it. But don't take heart. Every time I look at Bumblebees, I have to go and look on the internet, see how to read it again. Okay, so this one was left where it was. We're at 0.8. I'm going to take this voltage down a little bit less. And we're going to throw it into the bridge mode. Boom, it closed. The eye has closed. So it's not a 0.48. So we're going to go slowly around here to find... Oh, we're not finding any capacitance from 0.35 right there up past 0.5, 5, 6, 7, 8. Okay, it's not opening. What does that mean? Does it mean it's a bad capacitor? Yes and no. Don't you love those answers? Is it a bad capacitor? Yes, it is, but no, it isn't. Remember when I said earlier that the external, it's a good habit to keep this thing in bridge or in discharge so you don't forget. Remember I said earlier there is a the external generator switch. This is what I have connected up. I have it connected up to a wave, a model 185 WaveTech generator, and I've got a little bit of voltage on the output, which is being applied here. I have it set up for 10 kilohertz. The limit of this thing is 10 kilohertz, but I have it set up for 1 kilohertz. Now watch when I switch to the external bridge. All right, I go to the external bridge, so that I'm now using the WaveTech, and I close this. Oh, we have a little bit of window opening. Why do we have it now? Because we are using an external generator to power this capacitor, and the external generator has a little more oomph than this thing. So, well, and there's another very interesting thing to notice. If you notice, there's a very wide range. It's hard to get by this. Remember I went by this before and I could miss it? Well, you can't miss it with this. And look, it shows 0.6 microfarads. Is that a bad capacitor? Well, it's a capacitor. But what I can tell you is that the capacitance is off from 0.047 to 0.06. And because I had to go to an external generator, the dielectric is very poor. Okay? The dielectric is the insulator between the two plates of the capacitor, and it's absorbing electrons like mad, but it's not leakage. Every dielectric will absorb a certain amount of capacitors. Listen to me. Observe a certain amount of capacitors. Observe a certain amount of electrons, so that in this case, is absorbing so many I had to go to an external bridge. That's bad. That's a very bad thing. Now, what's interesting is if I change, well, notice how broad the range was, and I kept an eyeshadow going. You see what's going on here? That's bad. I mean, that just means this capacitor is leaky all over the place. Excuse me. It's got a bad dissipation factor, and that's what this is measuring right now, is a dissipation factor. So we'll go to the discharge voltage or discharge mode, and then we're going to set this up to 300. I don't know what the voltage of this thing is. I suppose I could take some time and learn it, but I know that the system voltage is on the radio around 300, so I'm going to use that. Go to leakage, and notice it closed, then opened. But what I want you to notice is it closed and didn't snap open, but it opened up a little bit of hesitation. See? Little hesitation before it opens. That dielectric was absorbing all the electrons it could from the potential across the terminals, and then it was satisfied. Okay? But that makes it very bad for radio electronics, because or any kind of electronics, because the capacitance now is not consistent, but with frequency changes. So, okay, here we are. We've tested this capacitor, and we've tested against the yellow, and we can see this thing it's a capacitor. It's way off on tolerance. This is 0.6 versus 0.47, or 0.06 versus 0.047. This one, the dielectric snapped right open. Let me show this to you again, just for the heck of it. Now remember, watch this one just kind of snap right open with very little hesitation or delay. See? That means that the dielectric is very efficient in this particular model. No delay. Okay. I was going to do the same thing with this 0.472 capacitor, 0.00472 a 0047 because it's 4,700 picofarads, so that's 0.0047 microfarads. And you can see this 472, 4 is yellow, violet is 7, and red is 2. So you're reading exactly what this capacitor says it is. Oh, it's so easy to know when someone else is showing you, hey? Anyways, the long and the short of it is these capacitors are all kind of yucky. So we take them out the radio. And they're out the radio, and now they're replaced. Let me show you another tester. This is a, I'll call it a cheapie tester. That's the best way to put it. And we're going to put this 0.047 into the terminals of this little ZIF zero insertion force socket, ZIF socket. We put it in here. We pinch it tight to connect it, and then we start it. Whoops. You can see it's testing, and it's a capacitor. It's a 45 nanofarad, 45.7 nanofarad capacitor, which is halfway between the pico and the micro. It goes pico, nano, micro. So it's a 0.0457 capacitance. Battery saver comes on. All right. Let's take this resistor or capacitor. I'm not gonna remember a darn thing, am I? And what we're gonna do, I'm gonna get you all confused by changing my terms. Let me get a. The only problem with this thing is you got to bend it to fit in here. So what we're going to do is we're going to shape our leads a little bit so that we can get it in the zero force insertion socket. There we are. Are we in? Nope, we're not in. And we'll stick this back in here. There's just not enough lead on this thing, is there? Oh boy, I'm sorry, but here we go. Well, let's see if we can get this to test. Well, it didn't. Oh, I had it pulled out altogether. Okay. This is not working at all. Do I have another 047 in here? No, but I'll use this 0047 because I've got more lead room here. I'm sorry for changing it up on you, but I thought the other one fit. So we'll put it in place. Start the test. It comes up with a 0.066 picofarad capacitor. 0.0066 picofarad capacitor. It's still bad because it's a 0.0047 capacitor. 472, and that's what that 2 is. It will read on here because this tester has a little more oomph than the Heathkit, a little more current capability. So it doesn't give me any idea about the quality of the dielectric material or insulator. Okay, so what have we done? We found that the capacitors in this, the Bumblebee capacitors, or Black Beauties sometimes are called, we found that these are no good. They all test this way, poorly, and I've replaced them. So now we can get on with the next phase of the radio work. And if you recall, I was going to test the tubes. Well, I did. And there was not one good tube amongst all the other tubes. So right now I'm looking for replacement tubes, and I'm going to do it on the cheap if I can, because it's just an old radio. And if I go to sell this radio, I'm going to go and fill it up with new or better tubes. Well, better tubes anyways, because a lot of those they don't make anymore. Is there anything else to talk about this tester? No, I don't think so. If you have a question, leave it in the comment section. I'll try to answer it. And anyways, that's it for this particular session. We've used the capacitor tester. We've realized the bumblebees are, in fact, bad little things. Replaced them with all polypropylene capacitors, and we're done. Oh, by the way, polystyrene has the best dielectric properties for your paper, mica, etc. capacitors. You can tell a polystyrene because they're sort of clear. The plastic is clear, and so when you look at it, you'll see the capacitor wound inside. Not very clearly, but you can see it. You can see it through the plastic, the clear plastic of the housing. Those have the lowest of all dissipation factors. Those won't approach mica capacitors for dissipation, or any other kind of mineral capacitor. Okay, that's it for today, Tube Timers. I hope you enjoyed this short session, and if all goes well, we'll be talking about the RCA radio in about a week or so. Goodbye for now, and take care.